All right, here we are in section 4, working with radicals and also rational exponents. So that word rational is coming back. Last section we talked about rational expressions. Word rational means fraction, and so now we're just going to talk about what happens when you have a fraction in your exponent. What does that mean? So first of all, just talking about radicals. Hopefully this is going to be more of a comfortable review for some of you. But I do have listed here some of the perfect squares, perfect cubes, perfect fourth powers. You guys all know that I have this up in my room, so it's nice to see it there. But since you don't have that chart, it might be helpful to write some of those down. So just kind of a reminder, how do we simplify radicals? Starting out with just a square root here of 252. What I like to personally do is I like to see which, since you're working with a square root here, we're going to look at what are the perfect squares and see which perfect square does 252 evenly go into. And so if we start out here is we will find out that, well, 36 works. So we can break this up into the square root. Let's do that a little bit bigger here. The square root of 36 and the square root of 7. So 7 times 36 gives us 252. Using this right here, that's going to help break this down because now I can take the square root of 36, which is 6, and we're left with 6 square roots of 7. Now, if you were to go along with this here, I suppose you could do, oh, do I have my calculator up? I don't think I do. 1 second, let me go and grab it. Calculator. Oh, that's not the one that I don't know which one I want here. Let's see which one I want. Get both of them loaded. It won't hurt us. All right, yeah, I didn't want that one. Okay. Clear that out. All right, so let's see. So 252, if like we were to take that by 4, that would work and we get 63. So what some of us might do is you might say, well, 252 is divisible by 4. So we do the square root of 4. And what did I say it was? 63. And so then we get 2 square roots of 63. The problem is that 63 can get broken down even further. And so that's where we start to run into these problems here. And so 63, we can break that up into 9 and 7. And so now you've got 2 square roots of 9 times the square root of 7. Square root of 9 is 3. So 2 times 3 times the square root of 7. Well, we get the 6 square roots of 7 that we started with. If you're doing kind of the guess and check method, start at the bigger values and work your way down. Okay. Try and see if any of those are divisible to begin with. Now, I'm going to jump down here. Actually, no, I'll stay at number 2 here. So we've got -5. This time we're taking a cubed root and we got 128. So what I'm going to do here is I'm going to look at my perfect cubes this time. And, starting at the upper end, I'm going to see which one of those is divisible. Can we divide 128 by? And so the one that's going to jump out to us here is 64. And now I can take this. I've got -5. And I can take the cubed root of 64. And 64 times 2 gives us 128. Now I'm going to take this cubed root of 64, that gives me 4. So I have -5 times 4 times the cubed root of 2. Well, -5 times 4 gives us -20. So -20 times the cubed root of 2 is what we end up with. All right, taking a look at a fourth root. So now you're taking a look at the fourth roots here. And these numbers grow really fast. So not too many of them work. But I'm going to start big, work my way down. Well, 48, not divisible by 81, but it is 16. And so I'm going to break this up. Pick a different color here. So I've got 2, which is out in front. I'm going to take the fourth root of the 16. And let's see, 16 times 3 gives us 48. So then I've got the cubed root, or sorry, fourth root of 3 left over. The fourth root of 16 is 2. So 2 times 2 times the fourth root of 3. 2 times 2 is 4. And then we have the fourth root of 3 left over at the end. So trying to figure out which perfect square goes into them. Now, what happens if you have variables that are attached to it? Well, variables, you're still working with, obviously, square roots, cubed roots. And when you take the square root of x squared, well, that is x. You're taking out groups of 2. If I have the square root of x to the third, that's the same thing as the square root of x squared times the square root of x. Well, square root of x squared is x, so you get x square roots of x. What I like to do here is I like to think about, well, how many groups of 2 are there? Well, there's, how many times does 2 go into 3? There's only 1 time, so I can take out 1x. I'd have 1 left over. Let's say you've got the square root of x to the 9th. Well, the 2 goes into 9 4 times. So I can take out 4 of those x's, which would leave me with x to the 4th, and I'd still have an x left inside. So here I've got the square root of 121, x to the 5th, y to the 6th. Now 121, well, that's a perfect square for us. So I have, and sometimes I might break it down. So I've got the square root of 121. I've got the square root of x to the 5th. I've got the square root of y to the 6th. All right. Square root of 121, well, that is going to give us 11. Square root of x to the 5th. 2 goes into 5 2 times. So I'm going to take out 2 x's, and I would be left behind with 1 of them. Square root of x to the 6th. 2 goes into 6 3 times, so I can take out all 3 y's, or 3 groups of 2. So now this leaves me with 11, x squared, y to the third, and the square root of x is what that now leaves me behind with. Now, when you're taking square roots, fourth roots, any even nth root, you do have to be careful because we, at this point, are not working with negatives. However, you can take an odd nth root of a negative number and be okay. The cubed root of negative 162, for example, okay? So I'm going to start out with breaking this up. So actually, I'm going to look over here to the right just to kind of have a little bit more space. All right, so I'm just going to talk about this cubed root of this negative 162 for a moment. And again, I'm going to take those perfect cubes. I'm going to start from the bigger values and work my way down. So let's see, we've got 64, that's not going to work. 27 does. Okay, 27 times 6. So I'm going to break this up into the cubed root of 27 and the cubed root of 6. Now the issue is that I have the negative. I'm going to make the negative go with that negative 27. Because when you think of some number to the third power that gives you negative 27, the answer to this is negative 3. So I can get negative 3 and be left with the cubed root of 6 then. You can take odd nth roots of negative numbers. As far as the variables go, well, 3 goes into 6 2 times, so I can take out 2 groups of 3, and 3 goes into 9 3 times, so I can take out 3 groups of 3. So now I'm left with negative 3 m squared n to the third, and then I'm left with the cubed root of 6 inside. Right, hopefully you were able to follow along with that. All right, over onto number 6 right here, you've got the cubed root of the 648. You've got that negative 2p out in front. Just again to give me some more room here. All right, so the 648, I'm looking for what perfect cube goes into that. And it looks like 216 actually works. So now I have negative 2p, and I've got the cubed root, I say 216, and 216 times 3, and I'm going to leave that p to the fifth and q squared here for a second. All right, so cubed root of 216 is going to end up giving us 6. So now I have negative 2p times 6. Right? Yes. And now I'm going to look over here. So 3, and I've got the cubed root of p to the fifth. 3 goes into 5 one time. So I can take out one group of 3, leaving 2 p's still underneath. And as far as the q's go, 3 goes into 2, doesn't happen, so I have to leave the 2 q's underneath. So negative 2 times 6, that gives us negative 12. P times p is a p squared. And then we're left with the cubed root of p squared, q squared. All right, so that right there is dealing with the simplification or simplifying of radicals. Now when we're talking about operations that take place, so subtracting, multiplying, and dividing, adding and subtracting is the one that's the most picky, because you need to think of it like dealing with like terms, okay? So when you talk about 2x plus 3x, well, that right there is 5x. If you take 2 square roots of 3 plus 3 square roots of 3, that gives us 5 square roots of 3. To be able to add radicals together, they have to have like radicands, okay? And that's what's underneath your square root. When I look at number 7 right here, I cannot simplify it as is. Okay, I've got the square root of 32, I've got the square root of 18, cannot be simplified. However, if I do break this up, and 32, we're working with square roots here, so we can do 16 and 2. And with 18, we could do the square root of 9 and the square root of 2. Square root of 16 is 4. 4 times negative 5 is a negative 20. Square roots of 2 then. Square root of 9 is 3. And 7 times 3 is going to give us 21. So 21 square roots of 2. When I add these together, I end up with 1 square root of 2. So all of that right there does indeed simplify for us. Taking a look at number 8, again, as is seen here, I can't do anything with it. I've got the 24, 12, and 54. But if we break all of these down, so 24, we can do 4 and 6, so square root of 4 times the square root of 6. Square root of 12, we can do the square root of 4 times the square root of 3. And square root of 54, we can do square root of 9 times square root of 6. Square root of 4 is 2. 2 times 2 is 4, so we get 4 square roots of 6 here. Square root of 4 is 2, so that's going to give us 16 square roots of 3. And square root of 9 is 3. 7 times 3 is 21, so I get 21 square roots of 6. Now I can't put all of them together, but I can do my square roots of 6. So 25 square roots of 6 minus 16 square roots of 3 is what we're left with. Same thing if you're working with nth roots, cubed roots for number 9, or even when you're working with variables at the end here. So with a cubed root here, I've got the cubed root of negative 56. I can go ahead and take the cubed root of negative 8 along with that. So we can do 8 times 7 would give us the 56. And 189, we could do the cubed root of 27 and the cubed root of 7. Cubed root of negative 8 is negative 2. Negative 2 times a negative 3 gives us a positive 6. So 6 cubed roots of 7. Cubed roots of, cubed root of 27 is going to give us 3. So that's 3 cubed roots of 7. So that's going to simplify for us. 9 cubed roots of 7. All right, number 10. We can that 42, we can break that up into 36 and 2. So I'm going to go square root of 36. I said 2, so I'm going to go x to the 5th. I'll leave that for there for now. Minus 3x, and 242. We could do square root of 121, and that would be times 2x to the 3rd. All right, so square root of 36 is 6. 6 times 4 is going to give us 24. Now, I also have that square root of x to the 5th. 2 goes into 5 twice, so x squared. Leave behind an x. Over on the other side, square root of 121 is 11. 11 times 3 is 33. And then since I'm taking the square root of x to the 3rd, I can take out one group of 2. That's going to turn this into x squared, and I'd be left behind with an x. So now if I combine these, 24x squared minus 33x squared gives us a negative 9x squared, square roots of x. All right, so that is the addition and subtraction. Now we have the multiplying part of it. You are definitely going to come into contact with this stuff later on. Plus, it's a good ACT review too. But what you need to be careful here of is that when you multiply, you need to distribute everything, okay? When you take something like 2x times a 2x, we get 4x squared. You're multiplying 2 times 2 and the x times x. Same thing is going to happen here. Now, here you got a negative 1. So I need to take negative 1 times 2, and then I have to take the square root of 18 times the square root of 20. Now, what's unique about this is just like how we take apart to simplify, we can put back together. Negative 1 times 2, well, that's negative 2. And then if I take 18 times 20, that's going to give us 360. All right. And what's ideally or most likely going to happen here is we can now break that apart. So I can go ahead here and take 36 times 10. Square root of 36 is 6. 6 times negative 2 is negative 12. So negative 12 square roots of 10 is what we would get here. Number 12, we're going to look at this part here. I need to take the 5 times the 1. So that's 5. And then I would have the cubed root. 36 times a negative 12 gives us negative 432. So looking and seeing, can we break this apart? Well, I can take the cubed root of negative 216, and I can take the cubed root then of 2. That would give us the negative 432. Cubed root of negative 216 would be negative 6. Negative 6 times 5, well, that's negative 30, and then you're left with the cubed root of 2. So hopefully some of this is coming back to you a little bit. How about 13 here? So 7 times 3, so that gives us 21. I'm working with square roots. I like square roots much better. 3 times 15, so that's 45. X times x to the 3rd is x to the 4th. X squared, y squared times y is y to the 3rd. So now we're going to break this up. Square root of 45, we can do 9 and 5. Square root of 9 is 3. 21 times 3 gives us 63. And then 2 goes, we got x to the 4th here, so 2 goes into 4 twice, so I can take out all x's. 2 goes into 3 once, so I'm going to take out one group of y's, and we're going to leave 1 behind. And I forgot my 5. Oops, I need to put a 5 in there, don't I? There we go. And then number 14, here's kind of where this idea of that distributing part goes that we have to be careful because we do have this quantity. So square root of 3 times the square root of 6, that's going to give us the square root of 18 minus square root of 3 times square root of 24. There's the square root of 72. So here we're dealing with multiplication, and now we're going to be working with the subtraction of simplifying. Square root of 18, I can go 9 and 2 with that. 72, we can go square root of 36 times 2. So it looks like we've got a 3 squared roots of 2 minus a 6 squared roots of 2. So final answer, negative 3 squared roots of 2. All right, how you guys doing? You hanging in there with me, hopefully? Again, I know this is a lot. Some of it you might be able to fast forward a little bit through, or hopefully like, yeah, I remember doing that, or even as you're looking at the assignments, you're ready to go. All right, 15 and 16, this one here, you need to remember your good old FOIL. You need to be able to multiply everything out. So you've got the 5 times 7 square roots of 2, so that's going to give us 35 square roots of 2. 5 times 1 gives us 5. Go to the inside here. I'm going to get negative 7 times the square root of 4. And negative square roots of 2 times 1 is a negative square root of 2. So multiplied everything out. Now I can do some simplifying. Square root of 4 is 2. So this right here is going to end up giving us 14. 35 square roots of 2 minus 1 square root of 2. So that's 34 square roots of 2. And 5 minus 14. And 5 minus 14, yeah, so that's going to give us negative 9. Now, if you did negative 9 plus 34 square roots of 2, that is completely fine. 16, squaring something. Don't just square everything. You remember you need to expand and FOIL this out. If there's something you leave this class remembering how to do is recognizing that you have to expand and then FOIL. 7 times 7, so that's going to give us 49. 7 times negative square roots of 2, or 7 times negative 2 square roots of 3, so that's going to give us negative 14 square roots of 3. Working the inside here, I get another negative 14 square roots of 3, and then at the end, negative 2 square roots of 3 times a negative 2 square roots of 3 is a positive 4 square roots of 9. Square root of 9 is 3, so 4 times 3 is 12. 12 plus the 49 that we have here. Is it plus 12, right? Yeah. So 4, so 61 minus a 28 square root of 3. All right, so we've got multiplying done, adding, subtracting, simplifying. Lastly, we have to talk about division, and this will definitely come around once we get into our unit on in our trigonometry unit, but trying to do what's called rationalizing the denominator. Okay, kind of one of those things that mathematicians we have these rules in place. Sometimes we just don't like to have square roots in our denominators, but it's really easy to get rid of. You really just need to create opportunities to get the perfect squares and cubes and fourth powers out of it. So here we've got 6 square roots of 248 divided by 2 square roots of 6. Now, what is awesome, if it happens, is you can sometimes do a little simplifying initially. And I love it when this happens. So 6 divided by 2, we can rewrite that as 3. Well, we can also here take 480 and divide that by 6. And that's going to give us 80. So really this simplifies down to 3 square roots of 80. And so now if I look at 80, well, that breaks up into 16 and 5. Square root of 16 is 4. 4 times 3, so that's 12 square roots of 5. So it's awesome when that takes place. Now I'm going to jump down to number 20 because it's not going to work for number 20. Here's where we rationalize our denominator, and you're just going to multiply the numerator and denominator by that radical. So I'm going to multiply the numerator and denominator by the square root of 10. This is creating a perfect square in your denominator because you have 10 times 10, which gives you 100. And then I have 5 square roots of 10 up on top. Square root of 100 is 10. And so you're left with 5 square roots of 10 over 10. Now I do need to double check here. We can simplify right here. So 5/10 is 1/2, so we get the square root of 10 over 2. That's what that simplifies down to. If we take a look at number 21, now I can take 6 over 4 and simplify that, but 8 over 3 doesn't do anything for us. So we're going to rationalize our denominator, and we're going to multiply the numerator and denominator by the radical. So I'm just going to do that square root of 3. This gives us 6 square roots of 24 over 4 square roots of 9. Square root of 9 is 3. 3 times 4 is 12. So I get 6 square roots of 24 all over 12. Now I want to do a little bit of simplifying here. That square root of 24 there, we can break that up into 4 and 6. And so this is going to give us, here, I'm going to go, what did I say? I said 4, square root of 4, square root of 6. Square root of 4 is 2. 2 times 6 is 12. So, I put in a big one. So 12 square roots of 6 over 12. Those 12s will cancel, and you're left with the square root of 6. Now, be careful when you are up working with, say, 18. Actually, no, they make 18 really nice for us here, because this is actually one that's gonna do some simplifying for us, which makes it really nice. And actually, I don't think we get too into them when it doesn't work this way. So here you got the 7/2. Then we've got the cube root. Now, negative 34 divided by 4 would give you negative 8. And so right there, the cubed root of negative 8 is 2. So 7/2 times 2, negative 2, gives you negative 7. So that's actually a really nice one. For number 19 here, we can do all the simplifying right away first to make our life a little bit easier. So 288 divided by 2, so that's going to be 144. J to the 7th divided by j squared, so that's j to the 5th. And k squared divided by k would be k to the 3rd. So just that right there worked out for us. 144 would be divisible by 8. So I can treat this as the cubed root of 8 and the cubed root of 18. Cubed root of 8 is 2, so I'm going to take out the 2. J's, j to the 5th. 3 goes into 5 once, so I can take out one group of j's. I am going to be left behind with 2 j's left over. And 3 goes into 3 once, so I can take out 1k. And there we have that. All right, I'm going to jump down to 23 and 24. When you have a binomial denominator, you have to multiply the numerator and denominator by the conjugate. We're going to see this also when we start talking about complex numbers. The conjugate is the opposite, and it's creating a difference between two perfect squares to eliminate that square root. So the conjugate here is -1 plus the square root of 5. And we have to do that to both the numerator and to the denominator. Up on the top here then, this is going to give me -4 plus 4 square roots of 5. On the bottom, you have to FOIL. -1, that's 1. -1 times the square root of 5 is a negative square root of 5. -5 times a -1 is a positive square root of 5. Negative square root of 5 times a positive square root of 5 is a negative square root of 25. Now you might be saying there's still square roots. Well, these square roots of 5's cancel out, and the square root of 25 is 5. So really we have 1 minus 5. Okay, so 1 minus 5 ends up giving me -4. So now I've got -4 plus 4 square roots of 5. Now, if I would not have distributed that, so if I would have kept that 4 out, which I probably should have just done, so 4 times 1 plus the square root of 5, I would see that those 4's cancel. And so I'm going to get a negative 1 plus the square root of 5 for our answer. And sorry, this should be a negative 1 up here. So negative 1. 24 then. I just got to see where I'm at on size. 30 minutes, okay. So for 24 here, I want to multiply by the conjugate. We would be doing the square root of 5 minus 4. And you have to do this to the top and the bottom so that it doesn't change the problem. Now you got to FOIL the top and the bottom. 3 times the square root of 5 is 3 square roots of 5. 3 times negative 4 is negative 12. Square root of 5, square root of 5 is the square root of 25, which I'm going to go ahead right there. I know that that's 5. Square root of 5 times negative 4 is negative 4 square roots of 5. Down below. Now, I know that working with these conjugates here that the middle terms are going to cancel out. The O and the I will always cancel out. Square root of 5 times square root of 5, square root of 25, which is 5. O and the I are always going to cancel. 4 times negative 4 is a negative 16. All right, so we are left now with up on top, negative 12 and 5, so that's negative 7 minus a square root of 5 all over 5 minus 16. So what that's going to give us negative 11. And if you wanted to, in this case, since everything's negative, I'm not super picky, but you could divide everything by negative 1 and get 7 plus the square root of 5 over 11. It's either one. All right. So there we are. What I think I'm going to do here is I am actually going to stop it here. And I don't feel like the rational exponents is all that big. And we'll be talking about that once we get into exponentials anyway. So let's just call it there for this section. Again, I don't want you to feel like you're getting overwhelmed. If you are, take a break. You just know that I'm here to help you and let me know which type of questions you guys have.